So now to kind of sort of look and get an example of how you would implement a function. Um, and in this case, I would like to implement a function whose domain is a cross product of two sets, and it's also a relation or a predicate that would basically give me a true-false output. I would simulate the game of rock, paper, scissors. So in the game of rock, paper, scissors, we have two players, and these two players effectively will simultaneously show their hands, and each of them will have the choice of selecting between a hand shape that represents one of these three choices: rock, paper, and scissors. So if you look at it, we can have two players, player number one and player number two, and each of them will draw a number that belongs to the set rock, papers, and scissors. So if I define the set D to be R, P, and S, representing rock, paper, or scissors, then the players could select a number, a value from this set. So player number one selects a P sub 1 element, and player number two selects a P sub 2 element. So P sub 1 and P sub 2 will belong to the set D. Now notice that this function, if I were to implement this function, it would take two values as arguments: value number 1, P sub 1, and value number 2, P sub 2. And each of these could be rocks, paper, or scissors, and rock, paper, or scissors. So as you see, then the domain of my function, actually let's call this B, set of elements, right? So then my function, its domain will be a cross product of B cross with B, and then the range of this function will be true or false. And let's actually represent these with the capital T for true and capital F for false. So T comma F. Okay. So how would I represent this function then? It's actually relatively easy. Since I have a cross product in my domain, so I will have a table, tabular format, for the elements that player number 1 chooses and element that player number 2 chooses. Right? So my domain is going to be from B cross B, so I'm going to have rock, paper, and scissors choices for one of the players, and rock, paper, and scissors for the other player. Now, the way that this implements according to the functionality for this game is rock beats scissors, scissor beats paper, and paper wraps rock. So I would say the function that I'm implementing is called beats. So my function beats that I'm going to implement, which is this F, it takes two numbers, P sub 1 and P sub 2. And then it returned a set of true and false choices. In fact, it actually returns 9 elements. So if player 1 is rock and player 2 is paper, then rock does not beat paper, so this is going to be false. If player 1 is scissors and player 2 is paper, then this is true because scissors beats paper. So then we'll just go on and on and on and fill these 9 elements in. So to show this function beats, how it actually works, another way to visualize this is with a table, a function table, that we can actually either represent our function with all these choices, or we could translate those choices into this tabular format, which gives me a better way of visualizing this function, especially because it's a k-array function. It's actually a binary function. It takes 2 elements. So we know that rock doesn't beat rock. So I'm actually going from this element down. So rock doesn't beat rock. Paper beats rock. Paper doesn't beat rock. Sorry. So that's going to be false. So paper does not beat rock. Scissors beats rocks. That's going to be true. Then rock wraps paper. So that's going to be true. Paper does not beat paper. And scissors beats the other way around. Yeah. So rock does not beat paper. And scissors beats paper. Wait a minute, what am I doing? Let's redo this. I confused. You may laugh. So rock does not beat rock. So rock does not beat rock. So this is going to be false. Paper wraps rocks. So this is going to be true. Scissors does not beat rock. So this is going to be false. Yeah. Notice that my p sub 1 element are the ones on top, and the p sub 2 elements are the ones in the column. Or I could have swapped these two, but it would just transport this function. So rock does not beat paper. Paper does not beat paper, and scissors beats paper. So this is true. And then rock beats scissors. So this is true. Paper does not beat scissors, and scissors does not beat scissors. So that's going to be my visualization of this function. I could have equally put the p sub 1 to be the columns here, and then the p sub 2 to be the rows. So let's say we have rock, paper, scissors, rock, paper, scissors. Then we go from here to there. Rock doesn't beat rock. Rock doesn't beat paper. Rock beats scissors. Paper wraps rock, so that's going to be true. Paper is false. Scissors is false. And scissors rock is false. Scissor beats paper, this is true. And scissors beats scissors is false. So as you see here then, just to show you how it actually visualizes. Just want to show you that this is effectively the transpose of these two functions are basically the transpose of each other if I just switch the rows and columns. So there, and there. So these two functions are basically transpose. Two tables are transpose of each other. So this guy goes there. This guy. Sorry, this guy goes there. This guy goes here. This guy goes up there. So that's how you will be able to actually evaluate a function, especially a function that comes from a finite set. For example, in this case, and a lot of the programs that we work with, or theorems that we work with, thankfully, because we're talking about computational devices and computational models. The machines are finite in terms of the number of states. So we would have a set of finite states, finite elements that represent our functionality, and so in this class you will see a lot of tabular formats that we work with to represent our computation, or models, definitions of computations we talked about. Now, if we look at this game of rocks, paper, scissors, you will notice that the rock, paper, scissors, you could evaluate it as a function that I just showed you earlier, or the function beat, basically, that scissors beats paper, paper beats scissors, and paper beats rock, and rock beats scissors, is a binary relationship, and so it's a predicate. So I could also equally represent this functionality as a predicate. So I would say predicate that I have here goes from the set rocks, papers, scissors, cross product with rocks, papers, and scissors onto the set of true and false. I could also represent this predicate, this game, with my predicate. And it will be easier to actually represent this game with a set. So I could say that this functionality is a set S whose elements are from, let's call this whole cross product D, whose elements are from cross product D. So as a result of this, each of these A's will be a binary pair, ordered pair, right? So each A could be, so an A could be things like rocks and paper, or it could be paper and scissors, or. One of the choices of the ordered pairs between rocks, paper, scissors crossed with rocks, paper, scissors. And then such that the predicate of A is true. So when I write my function as a set, then you can easily see, so out of all those, and let me just redraw again one of those tables. So let's say that this is piece of 1, this is piece of 2. So we do rocks, paper, and scissors, rock, paper, and scissors. So rock is false, rock, paper is false, and rock beats scissors, so this is true. Paper wraps rocks, so this is true. Paper, false, paper, scissors, false. Scissors, rock, false. Scissors, paper, true, and scissors, true, false. Okay, so I have 3 out of 9 elements that are true. So then this set S that represents beats, then it's going to be a product R comma S. So this is going to be the equivalent of R comma S, right? This is going to be the equivalent of P comma R. And this is going to be the equivalent of the set scissors for the first element and paper for the second element. So my set will be the set R comma S, P comma R, and S comma P. And as you see, this is much easier now to list the elements if I were to represent my binary predicate with a set instead of an actual function. So we could represent our relation either as a function like this with a table, or as a set like this without a tabular representation. When you have relations, for example, in the case that I had, for example, in the case of rocks, paper, and scissors game, the beats was a relation, right? So the beats was a binary relation. I could have said this, represented it with a beats function that takes player sub 1 and player sub 2, and then returns either a true or false. Or I could have represented infix. So this is, if you remember, I would call this a prefix notation. Or I could have used an infix notation. Or I could have used an infix notation doing this. B beats P sub 2. Okay. So I could use either one of these two ways of representing my relations. And so when I have a relation R, in terms of infix, if it's binary, I could say A, first element, relates to B, second element, right? So I could represent my relations like that. So with this formulation, we can talk about a special kind of relation. It's called an equivalence relation. If that relation has these three properties of it being reflexive, symmetric, or associative. Let's see what each of these mean. A relation is symmetric if any element from the domain of that relation is also in relation with itself. For example, if you look at the rocks, paper, scissors example that we talked earlier, this is not a reflexive relation because the diagonal element of my function, it's not true, which means that rock is not in relation with rock, so rock does not beat rock, paper does not beat paper, and scissors does not beat scissors. So if you have a relation in which every element is also in relation with itself, then that relation is reflexive. Let's see an example of a reflexive element or relation. Let's say that less than or equal to. So if I have a relation, let's say less than or equal to. Okay, and let's represent this relation with this with this symbol, less than or equal to. So I say that relation less than or equal to is a relation from n squared onto true false, right? So it takes a binary pair of, let's say, A and B, such that A belongs to the natural number and B belongs to the natural numbers, right? Then it maps this onto a false and true Boolean value. So if the first element is less than or equal to the second element, then that relation is true, otherwise it's false. So less than or equal to is a reflexive element, because for every element n in the binary in the natural numbers, n is less than or equal to itself, right? So we say that relation is reflexive. Symmetric is a relation is symmetric if you take two elements, x and y, and then they satisfy this condition. If x is relation with y, then y is also in relation with x, right? So according to this representation, then less than or equal is not well, actually it is a symmetric relation as well, because if I take a sub 1 from n and a sub 2 from n, then if a sub 1 is less than or equal to a sub 2, then is it the case that a sub 2 is greater than or equal to a sub 1 for every a sub 1 and a sub 2? So as you see here, this condition doesn't meet, because if 1 is less than or equal to 3, then 3 is not less than or equal to 1. So according to this condition, then less than or equal to is not going to be a symmetric relation, right? Whereas the equality is. An associative relation is a relation that satisfies this condition. If you take three elements, x, y, and z, then if x is in relation with y, and y is in relation with z, then x is in relation with z. Now, according to this condition, then the less than or equal is associative. So if you take a sub 1 from n, and a sub 2 and a sub 3, right? So if a sub 1 is less than a sub 2, and a sub 2 is less than a sub 3, or equal to, right? Then we know that a sub 1 will be less than or equal to a sub 3, right? So according to this, then this condition, then the less than or equal is an associative an associative relation. So if we have relation less than or equal, is it reflexive? Yes, Is it symmetric? No. Is it associative? Yes. Right? For the rocks, papers, and scissors relation, it is not reflexive, it is not symmetric. And let's see if it is associative. So if element A beats, let's see, if paper beats rocks and rocks beats scissors, then is it the case that paper beats scissors? Which you clearly can see that this is not the case. So, so rocks, paper, scissors games is not an associative relation either. So according to these definitions, then we say that less than or equal, as well as rocks, paper, scissors relations that we just defined, these are not equivalence relations. Alright, so let's talk about another example. And in this example, let's say that we want to define a relation on binary numbers, on integer numbers. And let's suppose that we make this relation to be this by definition. So let's suppose that, and let's call this like mod 5. Okay, so we call this mod 5 to be the relation from the set of natural numbers cross natural numbers onto true or false. And then we define this relation to be such that we say for a pair of I comma j that we draw from the n squared, we have I minus j mod 5 to be equal to 0. Or another way to say this is to say I minus j is equal to 5k for some k, an integer k, let's say, or rather an integer, so from z. And let's make these also from z. So we'll also take negative numbers as well. Okay, so then I'm going to go in here and make this also a from z set of natural set of integers. Okay, so we call this triple equal 5, and let's see if this is an if it is an equivalence relation or not. So first off, we want to check for symmetry. So is it symmetric? Is it reflexive? Sorry. So for reflexiveness, we want to say that if we have for every element I from the set of integers, I must be in relation with itself, right? So let's check, see if this is true. So let's pick I. We say I is in relation with I if I minus I is equal to 5k for some k that is an integer, right? So this is actually true because I minus I is equal to 0, which is 5 times 0, and so we found and 0 belongs to the set of integers. So reflexive, checked. So the equal 5 is reflexive. Now, is it symmetric? So let's pick an I from the set of integers and a j from the set of integers. And let's suppose that I is in relation with j, right? Now, this means that, according to the definition of my relation, I minus j is equal to 5k for some k. Okay? Now, we want to check and we want to see if j is in relation with I. Okay, I want to see if this is true or not. So we say j, this yields to j minus I, okay, which is negative of I minus j, which is negative of 5k, which is 5 times negative k. Now, since k I can't even spell, so since k belongs to z set of integers, then negative k is also in z. It's an integer, so that checks. So then we just proved that mod 5 is also symmetric. Now let's take a look at the associativity. For associativity, we need 3 elements. We need I, j, and let's say let's call them m, n, and u, right? So we pick 3 elements to prove associativity. We pick 3 elements. We pick m, n, and u from z. And then we start with the assumptions. We assume that m is in relation with n, and n is in relation with u, right? Then from here we want to see, is it the case that m, the first one of the 3, is in relation with u, the last one of the 3? Is that the case or not? So all we need to do is we need to prove, from here we need to prove that m minus u is some 5k, or something, right? It's a multiple of 5. So we start from the left hand side, so we know that m is in relation with n, which according to the definition of my relation, m minus n is some 5k sub 1. Then we know that n is in relation with u. Then from definition, actually, n minus u is some 5k sub 2, right? So if we subtract these two, so if we subtract the top one from the bottom one, okay, then I get m minus n minus n. Actually, add them. Let's add the two together. Plus n minus u, right? Which will be m minus n plus n minus u, which will be m minus u, right? Now from the top one, we know that this guy is 5k sub 1, and we know that this guy is 5k sub 2. So adding the 2 will result in 5k sub 1 plus 5k sub 2. So then from here, you just realize that m minus u is equal to 5k sub 1 plus k sub 2. Now since k sub 1 and k sub 2 are both integers, belong to z, the sum of the two belongs to z, because set of integers is closed under the addition. So then if we replace k sub 1 and k sub 2 with k, we just proved that m minus u is 5k, and that k is a member of z. So this just proves that m is in relation with u. So according to this, then mod 5 is also associative. So we checked for reflexivity, checked. Associativity, checked. and symmetry check. So then mod 5 is an equivalence relation. All right. The next topic that, or definitions that I would like us to get together is the concept of um, graphs. Graphs are visual representations of objects that have relations with each other, and so when we need to specify and visualize some of these kinds of objects, we can use either an undirected graph or a directed graph, and that would be effectively, or first let's talk about an undirected graph, or simply just a graph. It's a set of points and lines that connect these points. Each of these points, we call them a node. So in for example, if I have nodes that are usually represented with circles, so these are going to be my nodes in the graph, and then I connect these nodes with each other with lines. These lines then will become my edges of the graph. Sometimes we label the nodes, for example, node number 1, node number 2, and node number 3, and these will become the names of my nodes. So my nodes will be a set 1, 2, 3, and then edges will become an ordered pair, or an unordered pair for that matter, if you don't have an ordered graph. So for example, in this case, then my edges will be a set of binary sets. So 1 and 2 are 1 and 2 is an edge, 1 and 3 is an edge, and 2 and 3 is an edge as well. This will become my edge representations. Most of the time when we do something like this, then we represent our graph with a set itself. It would say set of nodes and edges. We could also abbreviate these with V standing for nodes and E standing for edges, which makes my graph to be graph V, comma, E. So that would be how I would represent my graph. Actually, graphs we usually represent them with a tuple. So it's going to be a sequence of sets V and E. The degree of a node is the number of elements that it's connected to. So for example, in this case, the degree of node 1 is 2, the degree of node 3 is 2, and the degree of node 2 is also 2, right? Because each of these nodes are connected to 2 elements. Whereas, for example, in this graph, all of elements have degree equal 3. Okay, so the number of elements that are, or number of nodes that are connected to a node, number of edges that emit from a node are its degree. If a node is connected to itself, we call it a self loop. So a self loop is when a node can also connect to itself. So sometimes, for example, and sometimes in this class you'll see that a node may be connected to itself. We'll call that a self loop. And this is pretty much it. Labeled graphs is when you actually label edges. So for example, if this graph was representing the cities that are connected to each other, you may represent the label of each node to be the distance between 2 cities. So we call this then a labeled graph. A directed graph is when you also have directions, and usually for a directed graph we represent its edges with sequences. So for example, if I have a sequence like this and a graph like this, a directed graph, then this graph, the way that I would represent it is that its nodes will be set of 1, 2, and 3, and then its edges will be a set of pairs, binary pairs, ordered pairs, such that the first element is the beginning of each edge and the second element is the end of each edge. So then this graph will be represented with that. And then my graph here, G sub 3, will be equal to this. Okay. And so that's how you represent a directed graph. A subgraph of a graph is a subset of its node and edges. So for example, if I were to represent this this graph, basically say that if I were to pick like these 3 edges, these 3 elements, and the connecting edges kind of like that, then so for example this then will be my subset of the graph. So 1, 2, 2, 3, and 3, 1. Okay, so then this graph G sub 5 will be a subset, so G sub 5 will be a subset of G sub 2, which is all the 4 elements, the whole graph. So a subgraph is a graph that's contained within another graph. It's the set of its nodes and the set of its elements are a subset of another graph. So that's pretty much all I want to talk about graphs. There are special kinds of graphs that we call trees. Or basically, a tree is a graph if it has no cycles. And a cycle is when you have a set of vertices that the start and the end vertex are the same. So if you have a set of edges that start from a vertex, go through a bunch of other vertices and go back to the same vertex that they started, this will become a cycle. So this is a cycle here, right? And if you have a graph that doesn't have a cycle, then you call that graph a tree. So trees, we usually represent them with something like this. You start from a root, and then you go down. And the elements whose degree is 1 are called leaves. So in a tree, leaves are elements or vertices whose degree is equal to 1. All right. And so basically, that's pretty much it. Before we finish up, I would like to talk a little bit about the concepts of strings and languages, and then go over some very basics of what strings and languages are, because they would be the bread and butter of computer science and the theory of computation that we will be talking about. And then talk a little bit about Boolean representation and Boolean logic. And then we'll pick this up next week in the next unit. I will restart discussions about Boolean logic, and then going through different ways and methodologies to prove the truth of statements, which we will be using sometimes in this class. So we'll start with languages. As I said, languages are the fundamentals and the building blocks of computer science. They are made of letters and or alphabets, and an alphabet is effectively a set of symbols. So the way that we represent these is that we say a language to be, so a language L is basically going to be a set of A, such that A is a string that's made of another set, and this set is called an alphabet. So when we talk about languages, we talk about sets and sequences. So a string is a sequence, and it is a sequence of symbols. Where do these symbols come from? They come from a set. That set is what we call an alphabet. And the set of all the strings that can be generated, we call them a language. So a language is a set, a big set, made of strings. Strings are sequences, and each element in the string, the sequence, comes from another set. We call that an alphabet. So, for example, and this is what we will show. Symbols are, we denote them with small letters or with numbers. Alphabets, which are sets of these symbols, we denote them with capital Greeks. And strings, we also denote them with italicized letters. And those will be sequences. So, for example, when I represent a set like this, 0, 1, then this is an alphabet. And we denote these with capital Greek letters, like capital sigma or capital gamma. These are the things that you usually see. This is called gamma. This is called sigma. So occasionally I'll refer to these by their names. So capital gamma or capital sigma are alphabets. These denote alphabets. How they look? They look like sets, just like you saw here. So a set of 0 and 1. So I could say that, or I could say gamma to be a set of X, Y, Z, and so forth. So notice that these are small letters, right? Small letters. Or numbers. So the alphabet is the Greek letter, which is a set. Symbols are small letters or numbers, which are the components, the elements of an alphabet. As a string, which I usually denote them with small letters, like a small omega or capital letter A, for example. These will be a sequence. So, for example, 0, 1, 1, 0, 1 is a sequence. Because for strings, orders matter, right? So for string 0, 0, 0, 1, 1, 0, 1, it's a different thing than, say, 1, 0, 0, 1, 1, right? So order in strings matters. So strings are effectively then, in that sense, they will become sequence of symbols. For simplicity, sometimes we just eliminate the parentheses and the commas between them. So for simplicity, I might write strings like this, or I might write strings like A, B, A, B, B, A, from the alphabet A, comma, B, right? So a string is a sequence from the alphabet that's made of symbols. Okay, so that's that, and then the language. And then language is set of all strings that can be generated by an alphabet. So, for example, English is a language, right? So English is a language which is a set of all strings from the alphabet A, comma, B, comma, blah blah to Z, right? So English is a language which is a set of all the strings that come from alphabet A through Z. Okay, so this is how we define all these. One important notation that we occasionally may encounter in this class is called the length of a string. So the length of a string, which we usually denoted with like two pipes, and then the letter that represents that string between them. is called the length of a string, and it is equal to the number of symbols in that string. So, for example, if W was A, B, B, A, then length of W is going to be 4. If U was 0, 1, 0, 0, 1, 1, 1, 0, then length of U is 1, 2, 3, 4, 5, 6, 7, 2, 4, 6, 8. 8. So the number of elements in that string is called the length of the string. Reverse of a string is when you spell the string backwards, and we denote that with superscript R. So if W was A, B, A, B, B, then WR, which is the reverse of it, it's going to be spelled backwards. So it's going to be B, B, A, B, A, right? If I have U to be 1, 0, 1, then its reverse will be the same. And these we call palindromes. Empty string is also a string, just like an empty set. An empty set is a set that does not contain anything. Empty string is a string with no symbols. So it's still a sequence, but it doesn't have any elements in it. So empty string, we usually denote that with small letter epsilon. It's called epsilon. Okay. And this denotes empty string. Okay, so as such, the length of epsilon is going to be 0 because it doesn't have any string. So epsilon, empty string, is something that you will occasionally also encounter in the class as an empty string. It has a very important role that it plays in the theory of computation. We can perform certain operations with strings, and so one of the important operations that we do with the strings is when we take two strings and we just concatenate them with each other, which means that we put the first one and then we attach the second one to the end of the first one. So if you have a string U sub 1 or U and W, both belonging to some alphabet, let's say gamma, which is coming from, say, letters A, B, and C, then the concatenation of U and W is basically a sequence where you get all the letters from the first element, and then this first sequence, and then attach them before the second sequence, right? So for example, if U was say 0, 1, 1, and then W was actually A, B, C. So you might start laughing again at me. So A, B, C, or B, and then string W was B, C, C, then concatenation of U and W, which sometimes we put a little dot in between them, and sometimes we eliminate that. The concatenation of UW, or we can also say UW, is going to be a sequence A, B, B, and then B, C, C. If for simplicity you said U was A, B, B, and W was B, C, C, then UW concatenated would be A, B, 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 C, C, right? Another example is, say, I have string B to be 1, 0, 1, and then string Q to be 0, 0, 1, then concatenation of V and Q would be 1, 0, 1, 0, 0, 1. Notice that the concatenation of VQ is not necessarily equal to the concatenation of QV, right? The lexicographic order of strings, and most of the time we use a modified version of it called short lex order, is basically like when you order your strings in a dictionary-like format. So for example, if we order our letters in the alphabet and give them some certain precedence over each other, so A comes before B comes before C, then if you order the strings in that alphabet or in that language, we call it it's in lexicographic order or short lex order if they're ordered in such a way that strings that come earlier, they're made of letters that come earlier in the alphabet. So for example, A comes before AA, comes before A, B, and all the strings with smaller number of letters or shorter strings come before longer strings. So this is short lex, when the order also takes into account the length of your strings as well. So I will actually go ahead and wrap up this this class. It's already kind of running up to about 3 hours that for the first week I'm having, or the first unit, that covered very basics of terminologies that we encounter in this class, mathematical notations, strings, graphs, sequences, sets, operations, functions, relations, and so on and so forth. And in the next unit, we will pick up with the concepts of Boolean logic and mathematical proofs. And then we will wrap up the mathematical foundations that we need to pursue this theories of computation and automata in this class. So, we'll start with the theory of automata and finite automata. So basically, I hope that you enjoyed this class. After we finish the theory foundations, which is the end of Unit 2, I will release the assignment, your first homework assignment, which will cover the concepts we talked about in this unit, and in the next unit, which will be your mathematical proofs. And then we'll keep going in formally studying automata and formal languages. I hope that this was an enjoyable first unit, and I will talk to you in the next unit. Thank you.